Okay, we've been discussing 1D systems and especially nonlinear 1D systems, for which it's seemingly not very easy to get a closed form solution or to get something that can be reduced to quadrature in general. And we were talking about the phase space of the system. System looked like this, and we found fixed points which were this, and then we said, you know, phase space looks like this, these are the fixed points. We drew trajectories that were coming one way or the other way, and then we had this analogy with the and so on, and found that there are some interesting geometric implications for first order differential equations. The most important one being that the first order autonomous system, no matter how complicated the nonlinearity, cannot really show any oscillatory behavior. Okay, that's a consequence of the fact that the phase space is a line, and the system trajectory has to go from one point outward, and it cannot retrace its path without the right hand side changing sign. We discussed some of this stuff, and also we identified the fact that fixed points can either be stable, unstable, or saddles. And we discuss conditions under which this will happen. Broadly speaking, you know, where you look at the fixed point, you draw f, and then you see where f is going up, down, is it positive, negative, and consequently y will increase, reduce, and so on. And based on that, we could say trajectories either approach these fixed points or they go away from the fixed points and whatnot. Okay, so that led to this stability business. And we also defined Lyapunov stability and absolute stability, and we said that this is, both of these are the same for a first order ODE, right? Now, the point where we will resume today is basically we will try to do this type of stability analysis, what is called stability analysis, finding out if fixed points are stable or unstable in a slightly more algebraic manner. Okay, now it's all perfectly fine for you to draw f of y in the function of y, and then you take it and do look at the sign, is it going positive, negative? That's fine, you can do that. But the problem is that as you go to higher order systems, that is not going to work. I think I mentioned that briefly. So you will be in trouble if you go to higher order systems. So we want something that's a little bit algebraic, okay, that we can generalize to higher order systems and use, let's say, for a second order system, and that's something we will do when we get to second order systems. Okay, so for that there is a very systematic procedure. It's a very simple procedure, and it comes up all the time. It's called linearization about a fixed point. Okay, so this is a procedure basically to determine if a fixed point is a stable fixed point, unstable fixed point, or a saddle. Those are the only three possibilities. We denoted them, we enumerated them last time. And linearization is very simple, like I said. So let's say y star is a fixed point. So f of y star is 0, so dy by dt is f of y. That's the system we're looking at, autonomous first order nonlinear ODE. And we say, okay, you take the actual trajectory, the actual curve, solution curve, y of t very close to y star. Okay, and then we'll see what happens to the trajectory as t increases. So will the trajectory come towards y star, or will it go away from y star? That's what we're trying to find. Okay, does it approach y star, or does it go away from y star, or neither, right? So if we do this systematically, then that tells us that if this happens, then the fixed point y star is a stable fixed point. If this happens, it's an unstable fixed point. This happens, it's presumably like a saddle point. Okay, so how do you do this? Well, there are only two pieces to this trick. The first is you redefine the variable. So you call eta is y of t minus y star. So this tells you the distance of y, how far it is from the actual fixed point. Okay, so you just change the variables. If you do that, d eta by dt is the same as dy by dt, because y star is a constant, you can't do dy star by dt is 0. And dy by dt is nothing but f of y, and f of y is nothing but, if I replace this, it will be y star plus eta. That's what f of y is. So I basically have the differential equation dy by dt is f of y star plus eta of t. Okay, that's my first order differential equation. Good. So now this term linearization obviously has a hint. This is also called linear stability analysis. That's a term you will see used commonly. And that means you just take this right hand side, it's a function of y star plus eta of t, you open it in a Taylor series. Okay, so you take this, expand in Taylor series. Okay, if you do that, then what do you get? You get f of y star plus df by ty add to y star times y star minus this, which is eta of t, plus half d square f by dy square at y equals y star times eta square, and so on. Okay, it's a Taylor series expansion. And so in the linearization, you drop terms that are not linear in eta. So you drop terms, these are higher order terms. And why can you do that? You can do that when y is sufficiently close to y star. Eta is the largest term, eta square becomes smaller than eta if eta is less than 1. Likewise, eta cube will be smaller than eta square, and so on. So all the successive terms will become smaller and smaller, so you can get rid of them, approximate them. And if you do that, then what you're left with is basically a linear first order ODE, which we know how to solve. So the linearized version is basically this. This is f of y star. Remember, y star is a fixed point of f, so f of y star is 0. So we'll get rid of this fellow. And so this gives us basically df by dy at y star times eta of t. This is a constant, of course, because it's evaluated at y equals y star, which is a constant. So it's not a function of t. So this looks like this. So you have d eta by dt equals k times eta of t. This is the linearized version of the original differential equation we started off with, and of course k is df by dy at y star. Okay, so that's what linearization means. You open the right hand side and linearize it close to y star. Okay. And remember what we said when we spoke about this first order. This, of course, we can solve in closed form. There's no big deal about this. You can just multiply and integrate. You get exponential to the power of kt. So eta sum eta naught exponential kt, and the key of this entire exercise is in k. So depending on whether k is positive or negative, which is the same thing as saying is f increasing, is f reducing, and so on. Depending on the sign of k, the eta will either blow up or it will go to 0. If k is negative, it will go to 0. If k is as t goes to infinity, of course. So as t goes to infinity, eta goes to 0 if k less than 0, or it goes to infinity if k greater than 0. One is exponential growth, one is exponential decay. Okay. So what that tells you is that go back to the original expression, y was y star plus eta. This tells you that the variable, the function y, whose solution you are trying to find, as t goes to infinity, if the sign of the derivative of f is positive or negative, y will either eventually approach y star, that is eta equals 0, or it will just go off to infinity. Okay. Those are the only two possibilities. So this tells us very clearly if a fixed point is stable or not. Clearly it's stable if you start close to y star and you reach y star. That's what we mean by absolute stability. And so if k, which is this guy, is negative, then eta will go to 0, and so the y star, that corresponding y star, is a stable point. Now remember, y star comes in here because you're evaluating the derivative at y star. Okay, so that's something you want to make note of. Okay. All right. Now, how do we evaluate this stability business? Let's do an example. Let's take up, I think I had this example the previous case. We drew this figure and we drew this a0 0, and then we said that this was an unstable fixed point and this was a stable fixed point. Right. So, we had stable, we had unstable, and then this is what it looked like. The same result can be obtained now using linearization. So, let us obtain same info via linearization. So, how do we do this? Well, first you find the fixed point, that is the first step. So, you have f of y star equals 0, you solve it. Okay. Then for each y star, linearize dy by dt equals f of y about y star, about y equals y star, and then look for the sign of df by dy or k at y star. Okay, it's a simple enough route. So let's try to see if we can recover this. Of course, this fixed points we have already found before. So the fixed points are y star is plus or minus square root of a by b. Those are the two fixed points, one on either side of the origin. If you linearize, the linearized equation is going to look, let's do it systematically so that I know what is going on. So if you linearize, then I write eta is y of t minus y star. I put this back in, I'll get d eta by dt is equal to df by dy at y star times eta. And now I have to do this for two fixed points, two of them that are separate. So if I take the first fixed point, the positive square root of a by b, then for that I am going to get df f is a minus by square, df by dy is minus 2by, and if I put y star is square root of a by b, get minus 2b square root of a by b, and this is negative because you remember we assumed that a and b were both positive over here. So this gives us df by dy at y star, which is a constant, is less than 0. Okay, and because of that, that means that if df by dy is 0, then this guy is less than 0, then this guy is less than 0. So you will have exponential to the power of minus something times t. So it will decay. So this point is stable. Okay, that's also what we found by looking at the sign of f. Right, that's what we found. This is stable. You can do it for the other fixed point as well. So you have this minus square root of a by b. Now you have df by dy equals the minus sign now cancels with this minus sign. So you get 2b square root of a by b, and so you will get this to be an unstable fixed point. Good. So we've been able to recover this visual picture just by doing some simple algebra, linearization, and this is a technique that will carry through no matter what order of ODE you're working with. Okay, so it's an important technique to learn, become familiar with. Good. Okay, now let's change tact a little bit. At the end of the previous session, I was talking about this possibility of fixed points sort of moving around and doing their thing and changing their position. Let's say, for instance, I have let's say I have an experiment. Okay, now this is not first order system because I've just said first order systems don't show oscillations, but okay, let's keep that aside for now and just talk about, let's say I have an experiment. This is a box experimental setup. Okay, it could be some complicated electrical equipment, and I'm basically measuring something. Let's say I'm measuring a voltage. Okay, this is connected to some sensors, let's say, and there is some process going on, something is happening, and these sensors are picking up stuff, and I'm looking at a voltage, but I'm looking not at voltage as a function of t, but what I'm measuring is t goes to infinity. So the transients that are involved in the sensors, the voltage fluctuation, so on, is very quick. And so every time I make a measurement, I'm making a t goes to infinity measurement of whatever the process is over here. It could be anything, it could be a flow rate measurement, could be temperature measurement, whatever. Okay, if it's temperature measurement, you're looking at a steady state temperature, let's say, and that's the thing that you're going to get. Now, this experiment has a knob, like all experiments, they have a knob, and there are various positions on the knob. Or now it looks like a radio, but okay, you have a knob that adjusts something in the experiment, and based on that thing, you get the measurement at the outside. Okay, so now I plot, and let's say this knob, I'm going to call the position of this knob theta. So it's a function of theta where the knob position is. It's like think of it like a fan regulator switch, right? I'm rotating it. I can rotate it by 180 degrees at each of these locations. I get a different value of some parameter. Maybe it's the pressure gradient in a flow experiment, maybe it's the heat flux in a temperature experiment, whatever. Okay, exact nature doesn't matter for now. It will matter later on. Okay, so as I keep changing theta, I keep measuring the steady state value over here. Let's say this is V. Now, initially the knob is in, let's say, theta position. I get some value of V. It goes like this, like this, like this, like this, like this, like this. And then the moment theta reaches some critical state, suddenly it shoots off to infinity. Let's say that's a possibility, right? So you're measuring, and suddenly you're changing the knob position. You're tweaking. Suddenly you see that okay, this V is gone off. Okay. Another alternative experiment is to maybe measure, you were measuring vibrations, let's say, and then you had some type of accelerometer that you were using to measure the displacements or the accelerations or whatever, and you continuously monitor the displacements, and then it's all in some stationary state, and at some point stuff starts oscillating. That's a different experiment that will correspond to something analogous. Okay, so here we just have one state, it's showing you this value, and suddenly it's just shot, it's gone off. Okay, at this point, which we'll call theta c, there is a qualitative change in the behavior. Okay, in this case, okay, it's trivial, it was finite, now suddenly it's become infinite. That's a qualitative change. Okay. So we're interested in things like this because they usually reflect something about the physical process that's going on underlying these systems. Okay, and so it's important to analyze a system like this. It's important to understand what happens when you change a parameter in the ODE. Now notice you are not changing the initial conditions, you are not changing the domain of the solution, you are not changing the ODE also, loosely speaking. The only thing you are changing is a parameter in the ODE. So for example, if I told you dy by dt, if you go back to our previous example, this would amount to changing, let's say, a and b. Okay, so I tweak stuff and then suddenly I see there is a big change in the steady state solution. So how do you analyze these situations? Now there is a systematic way to do this, and it just uses the same idea again. So you do linearization for every value of the parameter, and then you get stability, and then you see when the stability changes as a function of a and b, of course. But there is a nice way to plot it. It's called a bifurcation diagram, and the analysis is called bifurcation analysis. We'll do that. That's what we're going to do next. But the basic question is, how does changing a parameter, let's call it lambda. Okay, lambda is the general name that people will use. How does changing a parameter change stability of fixed points? Okay, that's a question. That's the quantitative version of this question. So let's go ahead and do that for this case. Let's take this example again. If I find df by dy, which is, remember, this is from the linear stability analysis, this is what, or linearization, this is what determined the stability of a fixed point. So for y star equals plus square root of a by b and minus square root of a by b. So what is the value of df by dy? It's minus 2by, so it's minus 2b minus 2 square root of ab. This is plus 2 square root of ab. Okay. So this one we already saw, this is stable and this is unstable. Now let's say I fix A. Okay, let me fix B. That's probably easier to understand first. Let me fix B and let me vary A. Okay. Now at the start we said A and B are both positive, but now we'll get rid of this and we'll say only B is positive. A is like my dial, I can rotate it and change it to any value, arbitrary value. Okay. Let's see what happens if you do that. The first thing that happens, of course, is that the nature of the stability which depends on A will change, and the location of the fixed points which depends on A will also change, okay, as you vary A. So I'm going to call A as lambda. Let's say I'm just for notational purposes I'm just using lambda. Then when lambda is positive, everything is fine, this thing just goes through, B is positive, everything is okay. Okay, same thing happens. As I bring lambda close to 0 from the positive side, then the moment lambda becomes 0, y star, this y star and this y star will come together and merge. Okay. Remember, when lambda is greater than 0, you have two distinct values. I am bringing them closer and closer as I lower A or lambda, both are the same. If I keep reducing A, those 2 points are coming closer and closer to each other. Okay. Exactly when A or lambda is equal to 0, those 2 points will meet each other and merge. Why do they merge? Well, because when lambda is less than 0, then in that case there are no fixed points, because this will become square root of a negative number. That's not real, so you don't have a real value of y star. Okay, you can represent it on the phase plane. phase space. So what is physically happening here? As I change the dial, if I plot, now I am going to make a different type of plot. Just to illustrate this, it's a little easier to visualize. I am going to plot the location of the fixed point. Remember, this is fixed point y star as a function of lambda. Okay, I am going to plot y star as a function of lambda, and the way I am going to do it is as follows. I have two solutions for lambda positive. So I will have two lines, one corresponding to this, one corresponding to this, and this one is stable, so I will indicate it with a solid line, and this one is unstable, so I will indicate it with a dashed line. Okay. So I will have two lines here. First line is plus square root of a by b, so it is positive, so that is the stable fellow, so this is a solid line, goes like this. Lambda is a, so it goes like square root of lambda. Okay, that is y equals square root x type of curve. And the second one is a mirror image of this about the lambda axis, so it looks like this. This is plus square root of a by b, this is minus square root of a by b, and this is unstable. Okay, so you now have two what are called branches, so these are called branches. This is branch 1, this is let us say branch 2. There are two branches of y star which come together as you lower lambda, and the moment you come lambda equals 0, they merge. What happens when lambda equals 0? We have discussed this case also. For lambda equals 0 equals minus by square, and if you remember, this had a saddle point. At y star equals 0. Okay. This one, if you draw the phase space, this is the y line, this is this, and this is this, and this. This is what we had, right? So this corresponds to lambda equals 0. The phase space looks like this. When lambda is positive, you have this and this. And when lambda is negative, you have nothing. You just have phase space, there are no fixed points at all. So if you start a trajectory here, it will go to infinity. Okay. Good. The critical value now, where the solution changes behavior qualitatively, the two fixed points are going away. That happens at this point, which we will call lambda equals lambda critical. And this point is also called a bifurcation point. Okay. And why are we interested in bifurcation points? Because bifurcation points fundamentally change the qualitative nature of the solution. Okay. This phenomenon that you will see, where you have the pairs of fixed points, one stable, one unstable, coming close together, meeting in a saddle point, is called a saddle node bifurcation. Okay. I'm just giving you these phrases, so you will keep seeing them again and again, and so you should know what they are, and you will use them for analyzing nonlinear equations in due course. But it's important to know the theory first before we can embark on applying the theory to stuff. Right? You should know how to analyze stuff before you begin analysis. So this is basically it. So this figure is called a bifurcation diagram. Okay. This is a bifurcation point or a critical point, critical lambda, and two branches in this phenomenon where you have two fixed points, one stable, one unstable, coming and meeting in a saddle, and then sort of annihilating each other. It's called a saddle node bifurcation. Okay. Now, I think it's important to make a few comments at this point. The first is, we already saw how the nature of the function determines if a fixed point is stable or not. And so, if you have a function that's going up and coming down, let's say a function that looks like this, if your f of y had something that looked like this, then you will always have one unstable point and one stable point. You could have f of y looks something like this, and again you will have one stable point, one unstable point. You do the linearization, you do everything, you will still find that you have a pair of stable unstable points. So really and these are for two, right? So you either have, you have one fixed point in, for example, the linear system had one fixed point, or some function that looked like this will have one fixed point, nothing else. But every time you have two fixed points, one will always be stable, the other unstable. Why is that? Well, because if this guy was unstable, then that means to the right of this f is negative, okay? And if there's another fixed point on this side, f has to be negative before you reach that other fixed point, because the fixed point is f equals 0, right? So it has to be negative before and then become positive after that. So every time you have a pair, you will always have one stable, one unstable, just by the very fact that the function has to cut the y-axis to have a fixed point in the first place. So this type of thing, saddle node bifurcation, is actually quite common in nonlinear differential equations, and I will give you some examples in the assignment that you can work out, which deal with some practical situations where you will see saddle node bifurcations. Of course, in a 1D system, again, these examples are a little bit of a stretch, they are a little bit cooked up, because most systems that we deal with that show very interesting bifurcations are usually second order systems. And nonetheless, it will give you an idea of how this stuff can be applied. But the observation that you have two fixed, if you have a pair of fixed points, one is always stable, one is always unstable, is a very important observation. Okay. And if you have a single one, you can have three possibilities: stable, unstable, and saddle. Now, just by the fact that any function should behave like this, and wherever it cuts the horizontal axis is a fixed point, just by that piece of information itself, we can start imagining what other types of bifurcations can happen. Okay, so if you look at the phase space, let's say for this guy, looks something like this, and presumably, okay, let's say even for this one, this example, as I change lambda, which is a, these 2 points will start approaching each other, and then when lambda equals a equals lambda c, that is 0, these two will hit in a saddle and they'll annihilate. So you can think of these, you can completely throw all the differential equation stuff out, and you can just look at these two as, let's say, two billiard balls that are coming towards each other as you change a parameter, and then the balls come and hit. When they hit, they merge into each other and they vanish. They sort of obliterate each other. That's one way of looking at it. It's a pictorial way of looking at it. And the reason I'm saying that is because you can use the same pictorial idea to try and understand what other types of bifurcations can occur, just purely from the imagination. Okay, we'll get to the algebra a little bit, but purely from your imagination, you can try and reason about other types of fixed points. Let me give you an example. If I had one stable and one unstable, let's say this one is just like this, different situation, not necessarily this. I mean, looks like this, but not necessarily this type of bifurcation diagram, just purely based on the imagination. I have one unstable, one stable. As I change the parameter, well, maybe this guy is stationary and this guy is coming towards this guy. Okay, and then sort of meets this guy and then overtakes this guy and goes off. That's a possibility, right? You could do that. Or this guy comes, this guy is here, both are approaching each other. They go past each other, but the moment they go past each other, the stable becomes unstable, the unstable becomes stable. That's another possibility, right? Just making up stuff. Right now, we're just making up stuff. So that's a possibility. So this guy comes, they come towards each other, they meet, and then after they meet, they part ways, but they've gone through each other. Maybe that's one. Why not? Yeah. And so now, if you compare this and this, the one that was initially unstable is now stable. The one that was initially stable is unstable. That's the transparent, billiard balls that go through each other and just pass through. That's a possibility. And there is a distinct change. There is a qualitative change again, right, from here to here. So this is also a possible type of bifurcation. It's called a transcritical bifurcation. We'll talk about that maybe in the next session, but we'll talk about that nonetheless. What if you had what else can happen? What else can happen when you have 2 points? You can either have them both come, hit each other and annihilate. You can either have them not approach each other, they're just going far away, which is fine. But there's no bifurcation because the only thing that's changing is the location of the fixed point. One is going away, one is going away, it's fine. I mean, they're moving away, but qualitatively the behavior is not changing. So if you started close to one fixed point, it's still a stable fixed point, you'll still go there, right? So that's not a bifurcation, that's not very interesting. That's the opposite of this, not very interesting. What else can happen? Well, you can clearly have them do the saddle node thing, you can clearly have them do this, pass through each other and go their own ways. But there's nothing else, right? There's nothing else that can happen in this case. You can't possibly imagine any other situation where these two sort of balls come and hit and do something else. Yeah. So it turns out these are the only two possibilities. Again, just purely based on the imagination, you can't really cook up anything else. But you can make things a little bit more complex. What if you had 3 balls? Remember, I said they come in pairs. What if you had 3? Is that possible? Can you have 3? 3 fixed points. We know you should always have, if they come in pairs, you have one stable, one unstable. What if there are 3? Well, that's easy enough. Without writing a single equation, you can just draw the situation out. All you need is a function that meets the x-axis, the y-axis, this one, 3 times. So 1, 2, 3. There you go. One fixed point, one more fixed point, third fixed point. So you can have 3 fixed points, just like you can have single fixed point, right? So what is the nature of this fixed point? This one, f is positive, it's going out. This one, f is negative, is coming here. So this is stable. This one, f is positive, it's going out. F is negative, it's going out again. This is unstable. Similarly, this one, f is negative, it's coming inward. This is f is positive, it's going inward again. So this is stable. So now you have 2 stable fixed points with a unstable in between. Still has the same principle when you have 2 of them. One should be stable, one should be unstable, but now you take 2 at a time. Take these 2 stable, unstable, take these 2 unstable, stable. They're still fine. Okay? As long as you can draw a function, you'll be fine. Okay? You can presumably also have the inverse of this. You have stuff coming like this and like this, which is fine. This is y, this now will be unstable because this is positive. This will be unstable. Okay, of course, it will go like this. This point will now be stable. And you have the converse of this for a function of this form, for a function of this form. So again, we're just drawing stuff because this is now a geometric problem. We can start drawing these things without writing down equations yet, but we'll see that there are very distinct equations that correspond to each of these. Okay. Now when you have 3, all 3 cannot be of the same type. You cannot have 3 stable nodes or 3 unstable fixed points or whatever. 2 should be of a kind and 1 should be different. and the two that are of a kind cannot appear next to each other because we know that from here. So, you should only have this possibility or this possibility. Okay. So, if you do that, now you can ask the question, what happens when I change a parameter in this case? Can we have a bifurcation in this case? And the answer is yes. As we will discuss, let us take this example for instance. As you change the parameter, these two could come approach each other. Okay. They could come and meet this guy and make this guy stable. That is one possibility. Or if you had the opposite one, where you had two unstable guys. Again, remember, I am doing all this just basically based on geometry, nothing. I am just cooking up stuff, right. What can happen here? Well, these two can come, they can come and merge with the center guy and then make the center guy unstable. That is a possibility, right. That also turns out happens. So, you can start making these possibilities up as and when you see fixed points on a line. Okay, that is the only thing you have to do. So, the problem is purely geometric, that is the long and short of it. Now, let us come back to this saddle node bifurcation in a minute, for a minute. The form of the equation we wrote down is actually a very interesting form. This one, it seems like, okay, this was a very special example. It just seemingly took it out of the air and wrote it down on the board, and then it showed this saddle node bifurcation. But okay, what does this have to do with any system, right? It turns out every time a system shows a saddle node bifurcation, it can be reduced to this form, close to lambda equals lambda c. Okay, so if I have a general first order differential equation like this, if it showed a saddle node bifurcation, then close to the bifurcation point, I can reduce this to this, something of this form for some suitable a and b. Okay, how do you do that? Well, now presumably f has this lambda dependence. Okay, so I will put that in explicitly, and I am going to open this in a Taylor series about lambda equals lambda c. Okay. If you do that, then I will get f of y, and not just lambda equals lambda c, I will also open it about a fixed point, y equals y star. Now, notice I am going to treat this as a function of two variables. F is a function of y and lambda. I am going to do 2D Taylor series. I am expanding about two of these variables. This is a parameter, it is not an independent variable, it is a parameter, but still, as far as the Taylor series is concerned, you have to expand about that. So, this Taylor series looks like this. And so on. So, I have opened this up in a Taylor series in the two variables. This is some arbitrary f, we do not know what it is. We only know that it has a bifurcation, saddle node bifurcation at lambda equals lambda c. Okay. So, since y star is a fixed point, f of y star is 0. So, that term goes away. Now, since it has a saddle node at lambda equals lambda c, the dou f by dou y evaluated at y star lambda c should look something like this, if you remember. It should look something like this. So, this curve, this is f of y, this is at the saddle node bifurcation point, this is y. So, since dou f by dou y is 0, this term also goes away. Dou f by dou y gives the slope is parallel to the y, and the f intersects the y at the origin. So, this term is also gone, and so in the vicinity of y star lambda c, the arbitrary, whatever so called arbitrary equation we started off with, is basically going to look like this, with the first leading order term will be this, second leading order term will be this. So, you will have dou f by dou lambda evaluated at y star comma lambda c times lambda minus lambda c plus half dou square f by dou y square, again evaluated at y star lambda c times y minus by c the whole square. So, these are the leading order terms. There are higher order terms, of course, which become smaller and smaller the closer you are to y star. Sorry, this is y star. Okay, and this is a constant, it's evaluated at a point. This is also a constant evaluated at a point. So, this is like some a times lambda minus lambda c plus b times y minus y star the whole square. So, you take any arbitrary differential equation ODE that shows a saddle node bifurcation, it is going to have a form that looks identical with this. Okay. So, if I just compare this and this, you will see that okay, small a and capital A coefficients don't matter, small b, capital B coefficients don't matter, but the lambda equals lambda c is encoded in here, y minus y star is presumably encoded in here. So, that's where the saddle node appears. It appears at y equals y star like this, and the saddle point, and so y star is clearly equal to 0 here, and so you can directly reduce any ODE system of this form to this. And remember what we said? We said that oh, maybe I should just make a statement about that. We said that a was our parameter lambda, right? So, a was lambda. So, the coefficient of this term is actually a, capital A, that is 1 in this case, capital A is 1. Lambda minus lambda c is just lambda. So, lambda c is 0. So, you get the critical point, the bifurcation point also. So, if you compare this with dy by dt equals lambda minus by square, then you get lambda c, this is lambda minus 0 times b times y minus 0 the whole square. So, you get lambda c is 1 and you get y star, oh sorry, lambda c is 0 and you get y star equals 0. Okay. So, any differential equation that shows a saddle node bifurcation close to the bifurcation point will have a form that looks identical to this. So, the same mechanism will be operative, and it sort of makes sense, because if you look closely at, let us say, a function that looks like this here, something that looks like this, let me draw it minus, let me just draw that, something like this, let us say. The moment I have a parameter, I change the parameter such that these points are coming closer to each other. If I come close enough, okay, if I come close enough, that basically, and if I zoom in here, it's basically going to look like a parabola. That's what this is saying. Okay. So, if I zoom in, if I get close enough to lambda c, then this is going to look like a parabola, and that's why this is reduced to this form. Now, deviations from the parabola, of course, are always there if you zoom out a little bit, and those deviations presumably are all there in the higher order terms, y minus y star the whole cube and things like that. Okay. Good. So, that is a saddle node bifurcation. So, this has a special name, it is called a normal form for a saddle node bifurcation. Okay, normal form. And if you have an ODE and then you manage to reduce it to something that looks like a normal form, then you are guaranteed that there is a saddle node bifurcation. Okay, let us take an example. Again, like I said, I'm just going to algebraically make up examples. Physical examples will be a little bit later on once we know a little bit more about this stuff, and once we do, especially the second order stuff. The example I'm going to make up is let me say y minus e to the power of minus y. Yeah, that's a good example. Let's make that up. Okay, this is a nonlinear equation. It presumably looks like that normal form thing if this third term was not there, but the third term is there, so it makes it different from that normal form. So how do you, the question we want to answer is, does this show any bifurcations? Okay, and how do we find that out? Well, first we find the fixed points. And the parameter is presumably lambda. This is the parameter, which again a physical parameter. It could correspond to some knob in some experiment, doesn't matter. So you first find the fixed points. What are the fixed points? Well, the fixed points are right hand side equals 0, so you have y star square is e to the power of minus y star. You have to solve this equation. Okay, it's a transcendental equation, so good luck solving that. So you're not going to get a solution in closed form, but you can solve it numerically. You can use Newton-Raphson or whatever to solve for it, or you can also solve it graphically. The way you do that is, oh, I got to do the normal form. Let me write the normal form here. For saddle node bifurcation, dy by dt becomes a times lambda minus lambda c plus b times, the factor of 2 doesn't matter. I'm just going to put it inside inside b for now, some constant, right? That's the novel form. Okay, so you go and you can plot this. Of course, you can plot this entire right hand side function, and if you do that, if you plot lambda minus y minus e to the power minus y as a function of y, which is what we were doing, then you will cut a curve. It looks like this in general, so you'll have two solutions. Okay, so that's a good sign. It looks similar to the parabola thing that we drew before, so that's good. But as you keep changing lambda, when lambda is equal to 1, it turns out you will get a curve that looks like this. Okay, it just comes and intersects, tangentially intersects this point at lambda equals 1. So this is good. So this is similar to what happens in a saddle node case. So we take inspiration from this and we say, okay, lambda equals 1 could be lambda equals lambda c, and so we expand, and it happens at y star equals 0, right? That's where the f of y star is 0, that's where it intersects. So you expand the RHS about y star equals 0, and you're going to get dy by dt is equal to lambda about y equals 0. Sorry, about to expand the RHS about y equals 0, and when y equals 0, e to the power of minus y you can write as 1 minus y plus y square by 2 okay. Okay, looks like the example is not a great example. Let me get rid of this 2. Okay, let's make this. The curve I think will still look similar. Actually, this curve will represent 1 lambda minus y minus e power minus y. Let's look at this equation. Okay, it's a little easier to do and it's a little late in the day and I'm a little tired too. So let's look at that. So we'll get rid of this. We've expanded the right hand side. We know that we've plotted the graph and we know that it's intersecting at y equals 0. And you open that second term out, you will get lambda minus 1 minus y plus y will cancel. So you get minus y square by 2 plus blah blah blah. This is dy by dt, and okay, this looks lambda minus 1 is like the equivalent of lambda minus lambda c. So you will get lambda c is equal to 1. That's what this is. And you will get y star equals 0. That's what you get over here if you compare that with that. Okay, so yeah, so please make this change. Okay, good. But okay, just some cooked up example just to illustrate the point that this is a normal form that you will always get when you see a saddle knot bifurcation. Okay. Okay, good. So while we're at it, let's also try to enumerate the other bifurcations that we spoke about. I'll give you the normal forms maybe in the next session, and then you can work them out by yourself. I'll give you an assignment to work them out as well. Okay. So take for example, so okay, let me enumerate that first. First one is saddle node. You have dy by dt equals lambda plus y square or lambda minus y square, doesn't matter, plus minus doesn't matter. For one, positive lambdas will give fixed points, for the other negative lambdas will give fixed points. That's the only difference, algebraic. So this one shows a saddle node bifurcation at lambda equals 0. This is the normal form. If I just use some values of a and b, which you can always do. The second one is what is called a transcritical bifurcation. And this one has dy by dt is equal to lambda y minus y square. This is another type of bifurcation. Let's see what this looks like briefly. So again, first step, find the fixed points. Here you will get y star equals lambda and y star equals 0. Those are the two fixed points. And second step, linearize about the two y stars. So if I did that, then y star equals 0, df by dy at y star is lambda minus 2 times y evaluated at y star equals 0. So this is lambda, and for the y star equals lambda fixed point, dou f by dou y at y star is lambda minus 2y, now evaluated at y star equals lambda, and this is minus lambda. Okay, so that's the second example. I've taken one, we've worked that out, we know what that is. Now I've taken this example. Turns out there's also a normal form, and this corresponds to one of the imaginative pictures we made with those billiard ball things. We'll see how. So I have these two values for this. Now again, the linearization tells us that whenever this is positive, it's a stable, it's an unstable fixed point. Whenever it's negative, it's a stable fixed point. So when lambda is positive, then y star equals 0 is unstable, and y star equals lambda is stable. Okay, from a fixed point of view. Okay, and again, I would encourage you to work through this carefully by yourself, so that you are sure of all the terms. I've of course seen this multiple times before, so I can just write it down. It's not very complicated. I would encourage you to work through it by yourself. Okay, so when lambda is positive, lambda is a positive number, this is unstable, this is stable. Now, if lambda is the tuning parameter and I suddenly change it from positive to negative, at lambda equals 0, what happens? Well, first thing that happens is when lambda equals 0, both the fixed points merge, just like before. So, you have two fixed points at the same location. They both become y star equals 0. And when lambda is less than 0, the opposite of this happens. When lambda is less than 0, what was originally unstable for lambda positive, when lambda is negative, will become stable. Okay, so now y star equals 0 becomes stable, and y star equals lambda becomes unstable. Okay, that's the situation we have. Okay. So, let us plot the bifurcation diagram for this case. Again, just analogous to what we did for the saddle node bifurcation. And again, I understand this material is fairly new. I am sure not everybody has seen this before. So, please take your time and work through it. The steps are fairly standard, straightforward. You only have to take derivatives and things. But the important point is you have to keep track of what the logic is. So, if you at some point lose it to logic and you are just randomly taking derivatives and saying stuff, then you have to review this material again. Okay. So, please make sure the logic is clear. So, again, bifurcation diagram is what you draw with lambda, with y star and lambda. So, you look at the fixed points, their positions as a function of lambda. And again, if you remember, this unstable I am going to plot with dashed lines and the stable with solid lines. Okay, so, if I do that, then y star is a function of lambda. If when lambda positive, y star equals 0 is unstable. So, y star equals 0 is this, it is unstable. When lambda positive, y star equals lambda is stable. So, that looks like this. Okay. When lambda negative, y star equals 0 now becomes stable, and this becomes unstable. Okay. So, this is the corresponding bifurcation diagram. This is called a transcritical bifurcation. Okay. And if you go back to that phase space, what was happening, this was the other picture we drew. We had one for positive, we had a positive value, this gave a stable. So, this is lambda greater than 0, this is the origin. Okay. For lambda greater than 0, you had this. As you kept lowering lambda, lowering lambda, lowering lambda, this guy started coming, approaching this fellow. Eventually, it came and hit. Okay. When it hit, this guy got stuck at the origin, this guy got pushed out. Okay. So, what was originally stable, unstable at the origin has now become stable because this guy came, hit this and moved it out. That is one billiard ball analogy again for this case. So, in the first saddle node case, two billiard balls came and hit each other and annihilated each other. Okay, that is extreme case of billiard balls, it never really happens, but okay, whatever. and in this case this billiard ball came and hit this billiard ball and displaced it. So it came and sat at the origin, the other guys got pushed out, and the other guy is now going to go for lambda less than 0. You can think of this guy coming and sitting here, and the other guy is now going out, right? Again, purely geometric imaginative picture that tells us what the possibilities are in terms of bifurcations. And this is a qualitative change. Again, this is a qualitative change in the solution, in the nature of the fixed point, because the origin initially was unstable, now it's stable, and the other fixed point away from the origin was initially stable, now it's unstable. Initially stable, now unstable. Okay, so that's why this point, again lambda equals lambda c equals 0, is the transcritical bifurcation point. Okay. Now you can ask, okay, what else can happen for a 2D system? Sorry, for a 1D system when you have two fixed points. Well, like we said at the start, there's nothing else that's really possible. You either have two annihilating, one hitting, other displacing, or the other is just hitting and rebounding, but that's not changing the nature of the solutions. What was, so for example, if I ask the question, what else is possible? I could draw these possibilities. So I could think of, let's say, one unstable, one stable. First this guy came and hit this annihilator, then second this guy came and hit this guy stopped, this guy moved. That's what this is. Now the third, I can say, okay, this guy is sitting here, this fellow comes and hits, rebounds and goes off. So this is for, let's say, lambda positive, and then lambda 0 it's hitting, and then lambda negative it's again going back. It's a possibility. You could think of this situation happening. Fixed points are moving. Remember, trajectories are not moving, fixed points are moving now. We are looking at the nature of the fixed points themselves. But this really won't correspond to a bifurcation problem, because the nature of the fixed points is not being changed. The positions are being changed. This came close, now it's going away, but its nature is not changed. It's still stable, right? This one, the position is changed and the nature is also changed. What was originally unstable is now stable, and vice versa, right? So this really won't correspond to any bifurcation problem. And what else can happen? There is nothing else that can happen, right? You can't imagine any other possibilities with two billiard balls on a single line, single straight line. So the next degree of complexity is you put three fixed points on a line. Okay, and I discussed that briefly. We'll talk about this more in the next session, but you have three of them. All three cannot have the same nature. They can't all be stable or all be unstable, because of the fact that f has to go in a certain way. So for instance, you could have this, or you could have this. You have three fixed points, and presumably as you change lambda now, two of them will move towards the third. That's perfectly possible. In addition to that, you could also have one of these situations. So if you change lambda, only two of them will move. So for example, these two could meet each other, annihilate. So you'll still have a saddle node. These two could move, hit each other, annihilate. You could still have a saddle node. So that possibility is still there with three. These two could move. For example, this could be stationary. This could move, come and hit this, and then do a transcritical. That's a possibility. So with three, the saddle node transcritical possibilities are possible for any adjacent pairs of them. These two or these two, these two or these two. But in addition, you could have an interaction between all three at once. Okay, that is called a pitchfork bifurcation. Again, the reason I'm putting these terms, like I keep saying, is so that we're familiar with these ideas and we know how to calculate them and work out the forms of these bifurcations, what exactly happens, and draw a bifurcation diagram. And the reason that is important is because when we analyze 2D systems, or when you analyze maybe PDEs or something at some point, you will see that Bifurcations happen all the time. Okay, they usually go from a steady state to unsteady state is through a bifurcation, just like this. Okay, so now the 3-ball situation looks interesting. 1-ball case, okay, was basically useless. It was just staying there by itself, and so 1-ball case, or one fixed point, ball being fixed point case, was okay, not interesting, no bifurcations. Okay, 2-ball case or 2 fixed point case, you had a saddle node or a transcritical. We worked out the normal form for both. 3-ball case, and of course for the 2-ball case you could also have no bifurcations. It's not necessary that you always have a bifurcation. So in the 3-ball case you add 1-ball case plus 2-ball cases. So you could have no bifurcations in the 3-ball case as well, that's possible. You could have a saddle node between any pair, like I discussed. You could have a transcritical between any pair, which I also discussed. Those 3 possibilities are there, but in addition you have this pitchfork. Okay, that is what happens here. So the pitchfork, all 3 will interact. 2 are interacting, nothing is interacting. Pitchfork, all 3 will interact, and the way in which they interact leads to 2 forms. This is what we will start off with in the next session. There's something called the subcritical pitchfork, something called a supercritical pitchfork. Okay. And it turns out that's it. You can go get 4-ball case, 5-ball case, 6-ball case, but you will seldom see any of them occur in practice. Even when you take a 4-ball case, you will usually see one of either this or these 2. Between pairs of them, between 3 of them together and so on. You will very rarely see 4 of them coming and interacting at the same time. That almost never happens. Okay, and 5-ball is even less likely, or 6-ball is even more so, and so on. Okay. So these are the only 3 cases where we have to look at and understand bifurcations, and it turns out when you go to study second order systems, you will have analogous bifurcations, you will have analogous saddle node bifurcations, analogous transcritical, analogous pitchforks, and so on. So those are all things that will be possible even in the second order case. Okay. So that's the reason we're introducing all of this right now. Good. Okay, so what we'll do now is in the next session we will look at this pitchfork bifurcation, because it's important from a practical point of view. Again, I haven't discussed any examples right now. It's been a fairly monotonous sort of discussion of this material, but when we do introduce applications, it'll be very clear to see where these bifurcations come up, how they influence the nature of the solution, and so on. But always please keep in mind the fact that we are again working with this hierarchy. So you have closed form, that was the first, and then the quadrature series business, and then you have the qualitative, and then the numerical. Okay, so most useful from a practical point of view to, well, not as useful as this, but certainly useful because you are getting a solution. Okay, so whenever you can't do either of these are the types of qualitative things you can say about the solution. Of course, if you have a closed form solution, this is fairly straightforward, because you will be able to write down when the solution changes nature, what the solutions are, and stuff like that, when there are fixed points and so on. But this information we're getting directly by doing the qualitative analysis that we've been discussing in phase space. Okay, so that's that hierarchy is important. I think I've been writing this down in every single lecture, but yeah, please make sure you remember this hierarchy. Okay, good. So we'll start in the next session by discussing supercritical bifurcations, subcritical pitchfork bifurcations, and then we'll list down all the normal forms and see some properties, and then we'll conclude our discussion of first order systems. Again, the main intent of discussing first order systems is to maybe figure out how to solve linear ODEs, and then to look at this complementary variation of parameters solution for the general non-homogeneous problem for the linear case, and then to look at these qualitative techniques that we can use in phase space for first order systems, and the fact that these geometrically lead to several interesting ideas about lack of oscillation, stability, and so on. Okay, so that's the most important thing to keep in mind. So we'll start off from here in the next session.